Hi everyone, my name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying to gather the view from the scientific community regarding high-performance computing to study turbulent flow, and with a focus in particular on the transition to exascale computing. So this podcast was launched with the ExCALIBUR project, which is a big 5-year initiative in the UK to harness the power of supercomputing, and the idea is to redesign the software landscape. This podcast is also connected to the UK Turbulence Consortium. So today we have an international guest from Australia, but who is very familiar with the UK landscape. It's Professor Richard Sandberg. So good afternoon, Richard.
Good morning, Sylvain. Good to see you again.
So Richard is as a chair of computational mechanics in the Department of Mechanical Engineering at the University of Melbourne, and his main interests are in high fidelity simulation of turbulent flow, aeroacoustic, and noise, and a lot of low order model algorithm, and so on and so on. So it's great to have him today. He was also heavily involved in the UK Turbulence Consortium when he was working at the University of Southampton. So I'm going to start, Richard, with my first question. For those who don't know you very well, or who don't know you at all, can you tell us a little bit more about yourself, where you're from, where you have studied, and how did you end up at the University of Melbourne?
Yeah, all right. So, originally I'm from Finland, although many people think I'm German, but I did move to Germany when I was pretty young, and then went to university in Stuttgart, where I studied aerospace engineering. And I was selected to go on a 9-month exchange to the University of Arizona to do one of my thesis works there, and I actually liked it quite a bit. So I stayed a bit longer and finished my master in Arizona, and then also did my PhD with Hermann Fasel at the University of Arizona. And after that, I came to Southampton as a postdoc initially, and then applied for lectureship, which I got, and then worked my way up to become a professor. And as you said, I was very well involved in the UKTC at the time. And then in 2015, I think, I made the move to Melbourne, where I've been ever since.
Great. Thank you. May I ask you, how did you become interested in studying turbulent flows and using high performance computing?
I think that really happened while I was in Arizona. When I went there, I was generally interested in fluid dynamics, but I hadn't really had much exposure to CFD and high fidelity simulation. But that was the bread and butter of Fasel's group, and he was mainly looking at transition problems. But I partly had to develop a new solver then for my PhD, and I really found it very exciting to be able to kind of code up algorithms that solve the equations that you can't solve by hand. And then when you get results and you start visualizing your results, and you see structures and you see everything happening in the flow, I just really found that pretty fascinating. So I kind of thought that's what I want to do more of, and that's what I'm still doing.
Great. So you said you have been studying in the US, in the UK, and now in Australia, working in Australia. So what's the best thing about your current position, and how maybe does it compare with other countries? I know the last couple of years have been slightly different, but what do you like about Melbourne?
Well, Melbourne is a pretty nice place to live for sure. Work-wise, I would say it's not that different to what the work was like in the UK. I mean, you're trying to do the best research you can, and you try to build a group of talented people that support you in doing that. So that's pretty similar. Obviously, it's also nice if you have a place where the quality of life is good. So that's one benefit of being in Melbourne. But also we have a pretty good group in terms of other people doing fluid dynamics. So it's fairly large. It's about 10 people that are interested in fluid dynamics, looking at different aspects, some more in kind of low order modeling, some in, doing experimental campaigns. And we all talk to each other, which is great. So That's definitely good. We have a good atmosphere, and I definitely like being here. I mean, the job in general, I think is great in a sense that you have the freedom to, pick and choose. Well, not always, but to do things that you want to do, and whether it's collaborating with certain industry partners or whether it's doing more fundamental work on certain problems. I just feel there's a lot of freedom there to kind of do what you're really interested in, and that's something I enjoy.
Great, thank you very much. Can you now briefly summarize what project you are working on? I mean, we will go into more detail in a minute, but just to give us an overview of your current research, that would be very helpful.
Okay, well, I would say it's broadly split into two parts. One is on the high fidelity simulation side, and we're looking mainly into turbo machinery problems, performing high fidelity simulations of individual blades. More recently, we've looked at even stages in compressors and turbines. And to make things even more interesting, we're looking at not only smooth surfaces, but textured or rough surfaces, which we probably could talk more about later. We've looked at some other problems that are related to turbo machinery, but more on the internal cooling side. So they relate to impingement cooling, trailing edge slot cooling. So a lot of heat transfer as well. And we've had a project just recently that was on high fidelity simulations of pulse jets. So it's basically a gas injection problem for a gas engine, which was kind of a new thing to look at, and obviously quite complex because it's a fully transient problem. So it's quite different. So that's on the high fidelity side. We also still work on some aeroacoustics problems. So one of them is looking at including flexibility of trailing edges to airfoils to see whether we can mitigate some of the noise that is produced. And that's really been a longer term activity to get all the ingredients together. So by now we can actually do serrated trailing edges where each of these serrated kind of teeth can move with the flow, or we can control its movement. So it has become a pretty complex setup. And this is what we're working on the aeroacoustic side at the moment. And the other part of the work is really more on the modeling side, where we're using our kind of in-house machine learning technique to try and develop or improve turbulence models. And we kind of look at the whole spectrum. So we look at RANS closures, and both in the context of the stress model, but also on the heat flux side. And we look at unsteady RANs and even LES modeling. So we're looking at separate trail modeling, again, both on the stress side and the heat flux side. And this, for different applications, depending on who the project is with. Great,
thank you very much. So for the first part of your work, where you are mainly focusing on doing high fidelity simulations, I was just wondering what flow solver you are using for your simulation. Just briefly describe the numerics and maybe the parallelization strategy.
Okay. So this is our in-house solver that I started developing back in Southampton, and by now there's been many cooks that have contributed to this code. It's a compressible flow solver that is kind of, by now it's fully 3D curvilinear, so we can do reasonably complex geometries. It has an immersed boundary technique built into it that is specific to compressible flows, and it has higher order capability, which is important for our aeroacoustics problem, but also some of the heat transfer problems that we're looking at on moving surfaces and blades. In terms of discretization, it's a find a difference code, and we have a choice of explicit or compact schemes. It's an explicit code in time as well, which obviously is not always a great choice if you go to high Reynolds numbers, but it is what it is. Makes parallelization easier though. And in terms of parallelization, it depends a little bit on what system we are running on. So we have MPI partition. We can have different blocks on different MPI processes, but also split the blocks into more MPI processes. And if we're running on CPU, we kind of have a hybrid MPI with OMP parallelization, so we can discretize, we can parallelize with the shared memory part as well. When we go to GPU, we're using OpenACC, so it's also loop-based parallelization that's combined then with MPI. And we have some routines that are also written in CUDA, simply because they are, you know, it was worth doing it because they're very, you know, compute intense ones. So we've gone through the trouble of doing that. And we kind of recently also put in an overset capability, which has actually helped us a lot for turbo machinery application. It makes life a lot easier in terms of designing good grids that wrap around the blade. But then, you know, when you have gaps between, you know, a stator and a rotor, you know, you can have Cartesian meshes as a background mesh. And then obviously there's a sliding plane as well for those kind of problems. So I guess in a nutshell, that's kind of the code.
Great, thank you very much. Right, so now let's talk about the second part of your work related to machine learning. I mean, you have made significant contribution to turbulence modeling using various machine learning algorithms. And well, once again, we don't have lots of time, but can you tell us briefly what are your main findings, and well, what's your approaches for improving turbulence model? But yeah, what's your main finding of your recent work?
Yeah, so we've developed again a tool that does the model development. We call it EVE because it's based on evolutionary algorithms. So it's ultimately a subset of evolutionary algorithm, which is called gene expression programming. And it basically allows you to evolve functional forms. So we start with a pool of kind of random functions that we can kind of just generate with some kind of, you know, it's an initial condition essentially, and then each of these models is you know, is tested, and you look at, well, you have a cost function, so you probably want to match you know, from a database your Reynolds stress or something else, and you see how well do all these models do, and you know, the best ones you keep and the worst ones you discard, and that's kind of our tournament selection, and then we go through all the usual steps of evolution. So these models can then mutate and they can combine, and we kind of keep changing them, and so we kind of iterate through generations, and if things work the way they should, the models get fitter, and by fitter I mean the cost function reduces and we get models that better fit the data. So that's kind of the overall approach. One of the issues we have grappled with, and I guess that's what a lot of others find, is that you can find models that are really good Reynolds stress models that approximate your true Reynolds stress pretty well from your database. But as soon as you plug them into your CFD solver, once they combine with the transport equations, and once you have the flow field from the RANS equations rather than from your high fidelity data, everything goes belly up. So one of the things we've done is to integrate CFD into the model development loop, so that every single model that is proposed and the candidate models that come from this gene expression programming tool are actually implemented into a CFD solver, and that happens automatically. You just send it a string. The CFD solver evaluates on a particular problem your solution for that candidate model, and then you kind of probe your cost function. So this has several advantages. First of all, you don't need a lot of data anymore because you have a CFD prediction from your candidate model, and you can simply look at the quantity that is of interest to you. You don't need full Reynolds stress volumetric field or something. You can actually just say, I want the shear stress at the wall to be right, or I want a wake loss profile to be right, or something else. So it is nice in that sense. But also the models are already being tested in the full RANS setup. So whatever comes out at the end is actually a model that, first of all, is stable, and secondly, produces a correct result in the velocity field, not just in the Reynolds stress field or somewhere else. There's just one little downside. You have to run many RANS calculations. And so that's where currently the problem is. As soon as you go to more complex problems or to higher Reynolds number problems, you know, the RANS evaluation itself becomes very expensive. And if you have to run, you know, thousands or tens of thousands of RANS, it's not possible. So This is something that we are currently trying to kind of figure out how to do that, how to kind of reduce the cost. But I think generally that approach to me is interesting because it is a full integration of the CFD and the machine learning. The other thing I think that is something that not only we are finding but others too is it depends very much on the input features. The success of your model depends on input features, and how do you choose the right input features? I think that's really where a lot of the thinking has to happen. And to me, well, we are using GP, others are using neural networks. Everybody has their favorite machine learning tool, but I guess it's not so much about the machinery that you're using. It's really more about, what are the questions you're asking the machine learning tool to solve and to address. And that's going to kind of, that's going to decide what makes a difference and what works and what doesn't. So I think we just need, smart people that understand fluid dynamics and probably have some idea of, the more analytical and fundamental aspects of turbulence modeling to just see the machine learning as a tool that you use to address some of those questions that we just couldn't address earlier. And now that we have not only the algorithms, but also more data than we used to have.
Great. And a more general question, maybe too philosophical, is: do you think overall that machine learning is going to be like a game changer for CFD, that we are going to be able to look at problems that were not thinkable a few years ago thanks to machine learning?
That's a good question. I'm not so sure. I mean, it'll be another tool in the toolbox, I think, of what we have. I definitely believe that we will be able to produce better models that can help us, do better design iterations or can be used in design iterations to really advance technology in some sense. But at the same time, I think even the higher fidelity simulation approaches are advancing in terms of computing becoming more ubiquitous, high performance computing, algorithms becoming better. I mean, there are some interesting things where people are starting to use these things like physics-informed neural networks and other things that are not really generating models, but they are, in my view, maybe I don't understand it properly, but they look to me as if they are a solver too. So you are basically feeding in some boundary conditions and whatever you have as information, and they basically find your solutions. Now, I just don't understand yet how expensive those approaches are going to be as well, and we might run into the same problem there. If we go to more complex, higher Reynolds number flows, maybe we are finding similar issues then to just solving standard Navier-Stokes. But I think, yeah, I mean, it's definitely an interesting time at the moment to see what's going on in that research area, and whether it's a game changer or not. Some machine learning techniques are also just rebranded things of the past. So yes. I think a lot of post-processing has been done previously, but I think the big difference now is that there is a lot more data available too, and that's where when these things come together, that's where we see more successes now as well.
Great. Let's talk a little bit about turbo machinery. So you wrote an annual review of fluid mechanics on turbo machinery. It's already available online. Can you tell us what are the main conclusions of this annual review? Where are we with blade and stage level simulations, modeling, and so on and so on? Yeah,
well, I think what we wanted to say is that turbo machinery is flows are pretty tricky. So there are definitely a lot of challenges there for modeling. So for examle, if you look at blade to blade interaction, you have very strong turning of the flow, and you have strong pressure gradients, and that quite often leads to a misalignment of the stress and the strain. So a lot of the currently used linear models will struggle to predict that. At the same time, turbo machinery always has a lot of deterministic unsteadiness on top of your turbulence, coming from blade row to blade row interactions, but also quite often vortex shedding from the blades themselves. And you know, with new machines becoming more compact, some of those frequencies from the deterministic unsteadiness move into the spectrum of turbulence. So that's again a big challenge for most models. So this is where high fidelity simulation really has been quite successful over the last 10-20 years, I would say, where we've been able to increasingly address some of those key challenges. And I think also with advanced post-processing tools and machine learning approaches, it has helped us improve closure models. So I would definitely say there has been quite a lot of fidelity CFD towards improving not only the models, but even guiding designs to be more efficient. And I think what really has to come next is to just increase the complexity of the problems that people look at. Most of these simulations, at least at the DNS or high fidelity or high resolution LES end, are still too simple. And we need to kind of look at more realism in the flow paths. You have to kind of include full 3D curvilinear geometries. There has to be things like purge flows, cooling, all these things. They all are essential in turbomachinery flows. Tip gaps. I mean, there's a whole list of things that as a next step, I think needs to be included. So, yeah, I think we've come pretty far, but there's also still a long way to go in terms of really kind of getting to the realism that designers really would like to see.
Great. Well, I guess that answers partially one of the questions that I had about exascale computers. So I guess if you have access to an exascale computers tomorrow, this is what you will be aiming for: more realism, more complexity, more features in your simulations.
Yeah. Absolutely, and I mean, it's something we're trying to continuously build up. So as I mentioned before, we have started looking at rough surfaces as well, or degraded blades that are not as smooth and nice anymore as they have been in previous simulations, and that obviously adds a lot to the cost. And we have been lucky to have 2 or 3 consecutive InSight projects over the last few years where we had massive amount of computing time on Summit, which is a kind of a pre-exascale system. And even there, we have to run things at a reduced Reynolds number with these rough surfaces because we just can't get to where we need to be yet. But that's I think the next step is once exascale is there, and well, as far as I understand, it should be there this year.
Yes.
then we can hopefully really look at machine relevant Reynolds numbers and flow conditions, with these more realistic surfaces as well. And of course, the list is long how you can then scale up your problem. You can just include another blade row, you can include end wall effects. You can make the problem bigger and bigger quite easily. So yeah, we're not going to run short of challenges when these machines are around.
Great. So I guess you also partially answer one of my question. I was about to ask you, where do you run your simulation? So I guess you managed to get access to the US supercomputers, but I was wondering what machine do you have in Australia as well?
Yeah, so well, I mean, we do some of our development work on local nodes that we have. We've tried to kind of get recent GPU architectures because we want to kind of keep working on the latest architectures to get the code ready and run on the bigger systems. And the university has a system here, which is called Spartan, which has, I think, of the order of 50-60 nodes that have 2 to 4, latest generation GPUs. So that's a good resource to, well, it's a good training ground for sure. And so Australia has 2 major centers. Basically, one is the National Computing Infrastructure that is in Canberra, and they have a system called Gardi, which is a pretty capable machine. I don't know exactly how many flops it produces, but it has a good number of GPU nodes too. And then in Western Australia, there's the Palsy Center, which has a machine that's currently being upgraded. So it used to be a machine that was called Magnus, that was a crate, and it was CPU only. So I think it was quite similar to the Archer 1 architecture. But now they are switching over to AMD, and it's going to be an AMD CPU machine for the first phase, and then phase 2 will come later this year, which is going to have a very large number of AMD GPUs. And we're definitely quite excited about that, because it's also happens to be the same architecture that Oak Ridge is going to have as their successor to Summit.
Yes.
So actually developing on that system is going to be good. In particular, we have so they have a code readiness project with a number of groups in Australia, and we're part of one of those projects. So they are partly funding a postdoc in my group to work on getting WIPSTAR ready for the AMD architecture. And we're still waiting to get access to the latest machine, but we're definitely working on the porting at the moment of the code.
Great, thank you. I had one last question about the Beverly Hill project. So can you tell us a little bit more about that?
Yeah, that's a project that we're involved in through some of the Office of Naval Research funding we have. So there's a number of groups in, well, I'm not sure whether they're all in the US, but we have been working mainly with Virginia Tech. They've been running an experimental campaign. It's essentially a smooth bump in a boundary layer, but at pretty high Reynolds number, and it basically is there as a challenge case, I would say, for CFD predictions. And our interest so far has mainly been in trying to develop RANS closures to better predict that flow. And I mean, it's a nice project in a sense because it's part of a NATO AVT project. So there's a number of groups being involved and working together. And we share data and we share experience. So yeah, it's an interesting problem. We haven't had the success yet with the turbulence models that we would have liked to have. It is a pretty difficult problem because it is a smooth bump, so you don't get a clear separation point. And if your models don't get the separation location right, then everything is wrong downstream of that. So and again, it's a very high Reynolds number. It's based on the height of the bump. It's 600,000. So that's it's not something we can easily just run an LES off to produce training data. So we are relying on having access to some of the sparse measurements that are available. And yeah, it's not easy to develop models on that case. But yeah, it's a good challenge, and it's definitely an interesting flow problem.
Great. And is the database is available to everyone, or it's just at the moment it's with your collaborator?
That's a good question. I don't think it's restricted, but I could be wrong. But there's at least 3 or 4 different groups running experiments, because part of the challenge is also to see whether actually all the wind tunnel experiments produce the same data.
Yes.
And just to see whether there are kind of installation effects or tunnel effects. So I would imagine, some of these groups are definitely going to be interested in sharing data with others too.
Great, thank you. I have a couple of more questions related on the high performance computing side. So you said you are going to be playing with AMD hardware, CPU, GPUs. I was wondering. I mean, this is a difficult question, but are you happy with high performance computing? Or is there anything you would like to change? I mean, are you happy with how GPUs or CPUs are working, or do you have any issues with memory, with data? What's your view on high performance computing as it is now?
I mean, generally I'm quite happy with the progress that's been made, right? I mean, it's quite amazing what compute we have available now. I think my complaints are more related to things like compilers and libraries. It seems that because we have a fairly exotic mix of OpenACC, MPI, OMP, every time we switch machine and use different compilers, we run into certain problems, and it turns out that there are sometimes even just bugs in certain compilers, and that can make life quite hard, especially if you have team members working on these problems that are not that experienced, and they think it's their problem, it's their fault, they have done something wrong. But otherwise, I think things are pretty good. I think one of the challenges that is becoming bigger and bigger is obviously the size of the data. So you can actually run a few billion grid point cases in a very short time, but then what do you do with all this data, right? And can you store it, and how you process it? And that I think that's just going to get worse and worse, because we'll be able to move up the number of grid points that we can compute fairly quickly, and I think the data processing aspect is not moving as quickly as running the simulations. And I guess the other thing, I think more from a environmental perspective, obviously what I would like to see is also a sustained effort in reducing energy consumption of HPC, and obviously that is something that everybody's looking at. And GPUs definitely have contributed to that. But yeah, I'm definitely interested in seeing how new machines using AMD architectures, not AMD, sorry, ARM architectures might help further reduce energy consumption, and so those kind of things are, I think, interesting as well.
Great, thank you. And my final question is, so we are talking about the exascale computers based on CPU, GPUs. What do you think is going to happen in 20, 30, 40 years in terms of compute? I know this is a very tricky questions, but do you think we are going to see a revolution with completely new hardware, so maybe quantum computers, or do you think we're still going to be playing with CPU and GPUs in 20 years?
Yeah, that's a good question. I'm not sure my horizon is that long, and I certainly don't have a crystal ball. I have been looking at quantum computing a bit, and we have a few people here at the university that are heavily involved in quantum computing, mainly in physics. And we've had a few discussions. I'm still not clear, how these quantum computers are going to be used to solve something like the Navier-Stokes equations, something deterministic. But who knows? Maybe we will all switch to lattice-Boltzmann-based methods, because you don't need to. I don't know. It's an interesting question. Of course, you never know, and whether it's quantum computing or whether it's something else that somebody comes up with in the next 10 years. It is likely, though, that we will see continuous increase in computing power, and even if we don't see a revolution, I think if things continue as they have, right, we will probably have another factor of 1,000 more computing power in, I don't know what it is, 10 years or something. So just imagine what we can do then, and give it another 10 years, and it's another factor of 1,000. So I think even without revolutions, we'll probably do things that we certainly can't think of now, and you would have to see how you actually exploit that. But it's interesting for sure, and I think one of the challenges is going to be to harness that power and exploit it, and so we have to continue working on codes and probably more and more interact with people from other areas that understand how to exploit those algorithms and architectures. I've lost you again. I can't hear you.
Okay. Sorry about that. Back. I'm back. Okay. Unstable connection. I was saying thank you very much for your inputs, and we wish you all the best for your future endeavors, for your high fidelity simulation research and your machine learning research as well. So, and I hope we'll be able to see each other in person, maybe in 2022. Who knows?
That would be nice, yes.
Anyway, thank you.
Absolutely.
Yes. Thank you very much, everyone, for listening to this podcast. As you know, you will find all the links on the UK Turbulence Consortium website. Just Google UK Turbulence. And we are also on Twitter, where we'll be posting the link on YouTube and SoundCloud. So thank you very much for listening, and hope to see you soon in a new episode of the podcast very soon.